Hey, honors chemistry. It's Tuesday, April 21st, and it's good to see you again. We're going to stop chapter 17 and not do the last couple pages. I'd like to invite you to take a look at that catalytic converter on 547 for interest, and I'm on 555. Let's do chapter 18 in 10 minutes. I'm being told that we're going to need to incorporate some ACT prep. And so I'd like to ask you to join my ACT Academy class. And I have put that on your class wall so you know my class code. I'm on page 555. We talked about reactions and how quickly they go to completion. And I had one arrow in that last chapter 17. And the not a two-way arrow. And so the reaction rate was equal to a rate constant. And then we've got the concentration of reactant A to the nth power times the concentration of reactant B to the nth power. And that was the rate law equation. And this time we're going to go ahead and expand it. If you were to take a look at page 557, you're going to see an equilibrium constant. This is the rate law equation. And now the equilibrium constant capital K. This is little k. This is capital K. Two different constants. Okay? The equilibrium constant is going to be this. That right there is going to be the denominator. Now, when we talked in chapter 17, we talked about the concentration of the reactants. Didn't worry about the products because it was headed always towards the products. It wasn't a two-way equation. But now it's going to be a two-way equation. So sometimes the products become reactants and it shoots back the other direction. And so we got to consider them both, reactants and products. And in the last equation, we talked about how quickly the reactants got used up. But in this case, once equilibrium sets up, the products could become reactants and they're going to get being used up, but they're going to produce more product, which is going to reverse it back to the other direction. And so we got to consider them both. And so if you take a look on page 557 in the middle there, you can see that the equilibrium constant is the concentration of product C to the X power and product D to the Y power. And then like this here, it's going to be reactant A to the nth power and reactant B to the nth power. And this is the way it is for an equation that is proceeding to the right initially. So it's like this. It's like N A plus M B yields, and don't forget, it's a two-way equation, X C plus Y D. Oh, really? So what are you telling me? I'm telling you that these powers are these coefficients. So if the equation looked like this, let's go on over to the next page. Let's go over to page 559. Do you see the equation at the top of 559? Hydrogen gas plus iodine gas. Green on this. This is hydrogen plus iodine. Hydrogen plus iodine yields hydrogen iodide. And the coefficients are 1, 1, and 2. 1, 1, and 2. So in order to get this equilibrium constant, we would go ahead and say reactant A has a power of 1. And reactant A is the concentration of hydrogen. And reactant B has a power of 1. And the concentration of the iodine. And on the numerator, it's always products divided by reactants. It's the product of the products divided by the product of the reactants raised to the power that their coefficient describes. So there's going to be a power of 2. And it's going to be hydrogen iodide. And there is no second product. And so if you look at the top of page 559, you'll see that concentration of hydrogen iodide squared over the concentration of the hydrogen times the concentration of the iodine. Now here it says plus on the equation, but up here it says times. So don't get that confused. All right, so that is the equilibrium constant expression. You put numbers in there because you've got concentrations of your reactants and the concentrations of what you're getting out of the reaction. And so you're going to have that constant. Now, can that constant be changed? Well, if it's a constant, it's a constant at a given temperature and pressure. But if you change the given temperature and pressure, you're going to change that constant. Okay, so you have to keep the conditions the same in order for it to be constant. All right. In fact, why don't we go on, since we're on 559, and look at the bottom of the page. And you can see that on the green strip at the top, it says 425 degrees Celsius. It's an elevated temperature, extremely elevated. And they don't say anything about pressure, but if you change the pressure, it's going to change that constant also. So if you change that temperature, it won't be 54.46 anymore. Okay. Now we're back to page 555. I've done 8 minutes already. It's hard to believe. Okay, so what is equilibrium? Well, equilibrium involves a two-way arrow. And so I'm going to go ahead and give you a reaction that I love to talk about in this particular case. The equilibrium expression goes like this. We've got page 564, nitrogen and hydrogen. Producing ammonia. Okay, and the coefficients are 1, 3, and 2. Got 2 nitrogens, you got 2 nitrogens. You got 6 hydrogens, you got 6 hydrogens. And it's a two-way street. Now, let's talk about equilibrium. Whenever we were dissolving salt, okay, there came a point in a closed system where the salt would recrystallize after it's dissolved at the same rate at which the salt would redissolve into solution. And it set up what's called an equilibrium. So when you put the salt in initially, it was just dissolving. But after it came to a point, there would be an equilibrium that would set up where the salt would recrystallize because the ions that are floating around in there were attracted to one another, and they would go ahead and fall to the bottom. But as soon as they do, then the water molecules would attack them again and bring them back into solution. And then they would recrystallize. And the rate at which it recrystallized was equal to the rate at which it would dissolve. So the dissolution equaled the recrystallization rate, not the amount, rather the rate. Okay, so we're talking about dissolution. Dissolving can set up equilibrium. We're talking about ionization. When this ionizes, this is vinegar. And you know, acetic acid is a weak acid. So once it forms a few ions, those ions rejoin again because they're opposite in sign. The hydrogen ion is positive and the acetate ion is negative, and they recombine and they go back to the molecular form. But as soon as they do that, they break down again into ions, and then it's back and forth once equilibrium has been set up for the particular conditions of pressure and temperature. If you change those conditions, then you're going to change how much will dissolve in solution and that kind of thing. There's another equilibrium system. Do you remember when we would have, well, it's called the triple point, and you can put water in a flask and you can evacuate the pressure, the air. And so it's really close to 0 atmospheres, and it's really close to 0 Celsius in temperature. And what you see in this system here, where you've got a vacuum pump hooked to it, and it's in a freezer, that you've got ice, and you got water, and you got vapor in a closed system because it's plugged up. And so it's reforming ice, and the ice is melting, and the vapor is condensing, and the water is vaporizing, and it's all doing this all at the same time. It's the point, it's called the triple point. It's the temperature and pressure at which H2O exists in all 3 phases. And it sets up what's called equilibrium. You remember us talking about that. So those are changes that are physical states of equilibrium. But this chapter talks about ionization constants for equilibrium. It talks about dissolution constants for equilibrium. And it talks about chemical equilibrium and reactions. And the one that I want to talk about is that reaction right there. It's called the Bosch-Haber process, and it's used constantly in industry. You got to know this. I'm on page 562. It's called Fixing the Nitrogen Problem. It's a good history lesson, and it gives us an opportunity to discuss equilibrium factors, shifting equilibrium. We call them stressors on equilibrium systems. Now, I know you probably are bored by now, and so I'm going to stop and grab some questions. I don't know what they're going to be. And tomorrow we'll pick up right here on page 562 about fixing the nitrogen problem. I want you to know that story just in case you work for Eastman. All right, see ya.